Okay, so this is the plan for today. We'll get started. I'll comment a little bit of the exam 1 briefing, but the key message is everyone did well.
Everyone reported.
My expectation. Okay. So not much else to say.
Not much else to say.
Uh, I don't know why I hear
I
it.
don't know why I hear it.
No, it's good.
That's good.
Yep. I hear an echo.
I think it's because Justin is not muted.
Yeah. Well,
I came in muted, but I didn't know that. Now I'm muted.
Muting should not be related to that. Otherwise, how in a meeting everybody can be able to talk, but sometimes devices are weird. But it's all good now. Thank you. Just if you have to mute, thank you for that. But anyway, should be a small glitch. Okay, we have more members. Great. And after I comment a little bit about exam 1, we will go into the prototype multi-layer perceptron model. Today's main content is to talk about the implementation from beginning to the end. So this is very similar to the first class of logistic regression or add-a-line model, where I will talk about the technical side. I like to flesh out the technical sides more quickly, but making sure that I cover everything important there. But after I talk about that, after I talk about the implementation technicals, I will be able to cover the intuition of neural networks. And most specifically, I think what will help here is for you to understand the advantages of neural networks, but not in the abstract terms, but seeing that perhaps, but still conceptually, but seeing that in a case that you should be familiar to see compared to single neurons, which is, conceivably is good at solving simple problems or less complex problems. Artificial neural networks are able to solve more complex problems. Through that business case, you can see the difference in terms of complexity. What does it mean really by complexity here? And in that respect, how does ANN provide the advantage of tackling the more complex problem than the single neurons? Logistic regression would be one example. Add-a-line is simpler, but logistic regression is more sophisticated. So hopefully you will see that. And I'm aiming to use 1/2 hour to finish whatever I have to say today. And let's get started. Any other questions before we start? If you have any questions about MLP, especially about technical sides, it's very likely I will cover it. So be patient. But I'll comment a little bit about exam 1. As I said, everyone exceeded my expectation for you. So I'd like to congratulate you all. You obviously have prepared well. That's why you can do well. So that's it. I think I try to provide comment that's directly related to how you did in my feedback to your exam. So based on those comments and because you have a copy of your exam, you can go back and try things based on my comment, and hopefully you get it immediately afterwards. I didn't have many errors when I grade the exam. Here's what I do mostly, and this is similar to how I grade the homework. I will run all the code cell in that order, um, to, because I won't rely on the output that the output of the cells that you saved in the Jupyter notebook, because that might be, that might not be in order, and you might have there might have some issues with the code that wasn't surfaced yet. So if there's any problem when I run the codes, it will surface. But in most cases, it's not a problem. In some other cases, some of you have already sort of closed. Some of you closed your Jupyter notebook and open it again and rerun everything in that order before you submit, and you saved it before you submit. That's perfect. Thank you for doing that. But still, I will rerun everything after I download your Jupyter notebook, just to make sure. All right. And then what happens if I found an error? If there's an exception? Rarely did I see an exception when I grade your exam 1, but occasionally, yes. Those things happen for different reasons. Sometimes you went back and forth to solve a problem, and eventually you got it, but forgot to update something in the previous cell. Because, when you solve the problem, things that you tried are stored in the memory. But those codes might have been deleted. So when you turn your work, and when I rerun the codes, whatever the codes that remain in the notebook, some of the variables might not be defined. And when I get to the point where you thought you solved the problem, but the variable was not defined in the remaining codes, I get an error. But I will carefully check the nature of the error. If it's a silly error, if it's a typo or things like that, I usually fix it first and make sure I get the code to work. And I judge the extent to which I have to fix the code. If it's a very minor code, the extent of the deduction is very minor, partial. Never have I deducted all the points of the entire question if it's a hands-on question, unless you left it blank. That's the only case where I deduct all the points for that question. So to the extent that if you tried, you would almost always get some partial points at least, and in most cases at least half of the points. So that's how I think overall, when you see the your scores of exam 1, that should reflect the state of your familiarity with those questions and the solutions. So overall, everybody did well. If you have specific questions, let me know. Because the feedback could be helpful, I didn't post the answers because that might not be necessary. But if you need to discuss a specific question, let me know. We can schedule a meeting to talk about those. So that's all about exam 1 I need to say. Any other questions? Otherwise, exam 1 is done, and we can focus on the rest of it, the rest of the course. Good? Good. And again, congratulations. You can expect the same formality for the final exam, exam 2, just the coverage will be different. But again, let me alert you that from this point on, I think I forgot my notebook. From this point on, things will be more complex, as you can expect. Neural network is more complex than legislative regression. So implementing neural network is more complex. There are more steps. Some of the steps are harder to conceptually understand, less to also understand the codes, because those two are related. The order of things also matter, and the amount of codes are longer, obviously. that's one level of complexity. So that's for neural network. And what comes next is the model evaluation. That's just one lecture, limited content, but the topic is both important and a little tricky to understand. You know, false positive, false negatives, confusion matrix, and those things. And what comes after that is unstructured data. So in other words, it's not natural language processing. Be prepared for, you know, data that require extra care in terms of cleaning them. So it's entirely different kind of mentality to deal with text data. But still, with more complex topic and more complex data, which is the text data, natural language processing methods, you get to deal with very interesting business cases. I'll just let you know that I collected, not particularly for this course, but for the past year, for some of my other research, I collected a massive amount of data from Yelp. So I used data scraping frameworks and methods and tools to download data from Yelp. And in the meantime, sort of designed a process and a framework to specifically, smoothly collect data from Yelp. Yelp now is a mature tech company, although some say it's declining, but its web architecture is very good and sophisticated. So that means more challenge to collect massive amount of data from Yelp compared to other websites. They have better ways to prevent massive downloading and scraping of their website, and this is obviously understandable, and I understand that. But you know, for research and also teaching purposes, I also need a real massive amount of data. So sorry, Yelp, I have to say that. But Yelp has participated well, even by doing nothing, right? So we want to acknowledge their contribution there. And by working with Yelp data, and it's a large amount of data, you'll be working with 100,000, more than 100,000 rows of data. That's actual Yelp reviews for businesses. You get to deal with the real life textual data problems by using NLP methods, state of the art, and learn about the processes of cleaning the data, and also learn about a method which is you know, one of the machine learning methods that we talk about, the unsupervised method, to extract patterns from these textual data. We call them documents. So it's going to be different. All that you have learned about implementing single neurons and multi-level neurons may not be applicable there. So it's entirely new stuff, but it's very exciting and real data and large amounts of data. So because these two things are more complex, the final exam will reflect these. Hopefully it's both challenge. It will be challenging, but without challenge, it's not interesting. It will be both challenging and interesting, but I will use the same way to guide you through all these materials. By the end of the course, you'll have learned both the supervised and unsupervised methods very well, and you can do real projects after that. So that's about, you know, a little bit of looking forward to what the exam 2. So no questions about exam 1. We'll move on to talk about MLP implementation. Yeah, go ahead. Great, thanks. All right, so MLP. Last time I stopped at only I was beginning to talk about forward prop, but then was a little short on time, so I talked about exam 1 in the previous lecture. So I'm going to continue from forward prop, but here is the overview of the process. As you see, if you compare this to the logical regression, it's longer process. The most noticeable difference is with backprop. There was 4 short steps. Now there are 4 longer steps. This is mostly because of the additional layer. The sort of the trouble or the complexity added by the additional hidden layer is, you can say, it's massive if you compare to the single neuron. So that's where I will spend the most amount of time. But within the backprop, the step that causes the most amount of time is this one. The step of calculating the error of the hidden layer. This is the sort of with the gradient already explained. This is the sort of the gist, the identity of the backprop for the multi-layer perceptron model. After you have mastered these processes, understand the inner workings, and be able to implement them and even debug, if I hand you a piece of code that has problem in it and ask you to debug and fix the problem there to make it right, to train a 3-layer multi-layer perceptron model, then you should be able to, by yourself, to develop the codes or to modify the codes for a neural network that may have 2 hidden layers compared to 1 hidden layer. So by then you should be able to add a layer to your codes and implement a more complex, a deeper neural network, if you will. But again, being able to implement a neural network, a complex neural network model, even deep neural network model from scratch on your own by using NumPy, doesn't mean that you need to use the codes. In the end, ultimately, I will advocate that you use open source packages, libraries, TensorFlow, even scikit-learn is faster, but not as good. TensorFlow and Keras is better. You also have other, emerging libraries. Use those to tackle real problems. In a learning process, use NumPy and implement from scratch. All the other things are similar. So I will go right into, again, the data set is default to pre-processed. It comes with 4 data sets. It's already splitted and pre-processed. There's no need to pre-process. So let me talk about the forward prop. To sort of understand, and by the way, the cheat sheet should be, keep it handy. The cheat sheet about with the handwritten notes about the implementation and the formula, also the linear algebra equations that maps with each line of the code should be helpful. assume that you have those. And on the side are a list of most important or key variables in the steps that I will refer to. And the most difficult part is to sort of have a quick reflection about the dimensions of each of these matrices in the process of implementing the model, as well as a better understanding of what does each row mean and what does each column mean in each of these matrices. And that's what I will focus on mostly here, is to explain what the structures and the elements, what do they mean in terms of the neural network model. So forward prop, let's use this. Let's refer to the flow. This is the prototype structure. We have 3 layers: the input layer, hidden layer, output layer. There are different numbers of units or neurons in each layer. So we need different indexers. To refer to the input variables, input variable x, x1, x2, x3, I use index j. You typically start with I, but I is reserved for the number of cases, number of rows in the input data. So I is not available, so I use j. J refers to, you can think of it as, starting from I, j, k, l, it's a sequence, and j refers to the input layer, refers to a specific unit. J indexes the input unit, and it can go up to m, because we have m number of input variables. And k indexes the hidden unit. It can go from 1 to d. D is the number of units in the hidden layer. This part you specify, right? For this example, I specify D to be 7, I think. 7 units in the hidden layer to be reasonably complex, but not as too complex. We use L to index the output unit, and it has up to T unit. This T directly related to the number of discrete labels in your Y data, in your target data. In our case, the fall only has 2 labels, so T is 2. So there are only 2 output units. Right? Right, given these, we have the X data set, and a bunch of coefficients W and B are coefficients, A are activated value of a particular layer. So with that, I can talk briefly about the forward prop. There are only 4 steps in the forward prop in one epoch. You go from the hidden layer to the output layer. You do hidden layer first, because it's the flow is from left to right. Hidden layer is the first layer that you deal with, right? In each layer, there are 2 steps. You calculate Z, you calculate A. Calculate Z and A, but it's for a different layer. So we use different postfix to identify the layer, the specific layer. We use _H to identify the hidden layer, and _out to identify output layer. You can also use _O. But for now, I use out just to be more clear. So you postfix that with the layer notation. You get the specific, you get the specific name for that variable for the specific layer. All right, and for Z of the hidden layer, let's look at the graph. For Z of the hidden layer, for each unit, let's take 1 unit as an example. It is simply the sum of multiplication between the input variable and the weight. Each line is a weight, right? So that's the um, you multiply the input variable with the weight and plus all the other multiplications plus the bias term for this particular unit, you get a linear combination, the net input for the hidden. But now we need to do it for multiple units. We used to do it only for one unit for a single neuron because of single neuron. Now we have to do it for multiple units. So the structure of the net input function, the net input values changed. We used to have only a column. We used to only have a vector. Now it becomes a matrix. And so let's spend a little more time on this. So Z, let's think about it. For the first unit, we will use the input data and the weights pointing only to the first unit. The weights for the first unit is stored, that's the weight of the hidden layer. It's stored in the first column. There are D number of columns indexed by K. K indexes the hidden unit. So there are D number of columns. The first column of this weight matrix corresponds to the coefficient that will be multiplied to each of the M variables. We have M variables, right? So X data set and the weight of hidden layer is directly related. Number of columns of X correspond to the number of rows of the weight matrix. That makes sense? Hopefully that makes sense. Okay, so that's the first unit. But the first unit is not a single number. The first unit will calculate an entire row of data. Hold on, an entire column of the data. And here is how. You take the first example in the training set, which is a row, right? A row in the training data X. There are M elements, which means the M variables, age, gender, income, whatever, of that particular I case, which is a customer. If you times X and weight of H, you are going to first calculate the first element of this matrix, which will be the result of multiplying the first row of X with the first column of weight. Each of the elements that corresponds to the same position will be multiplied, right? And then summed together. So that's a net input, linear combination function. With all these calculations, you get one element in the Z net input matrix, right? And keep in mind, the column indicates the hidden unit. The rows indicate a particular sample or example. So the first element is calculated. You go down to the second element of the first column. What does it calculate? It calculates the value of the net input of the first hidden unit, still the first hidden unit because it's the same first column, of the second customer example, I equal 2, which is using this row of X, but using the same first column of the weight matrix, to calculate the linear combination, which is the net input for the second customer on the first hidden unit. So after you calculate everything in the first column of the net input matrix, what does it become? It becomes everything. Let me switch to the next slide. It becomes everything in this node. This hidden node or hidden unit or hidden neuron, it's a vector, it's a column vector. Its value is stored inside this matrix in the first column. So now you understand how does the rows of the X input data set and the columns of the weight matrix of the hidden layer, how do they come together being calculated and be transformed into the different values or different rows and columns of the net input function in the hidden layer. Does it make sense? Any questions?
So, so you're saying the first vector in the input layer is also the entire vector in the hidden layer?
Yes, everything in one unit, in one of the units. The first unit is going to be the first column, and so on and so on. Its dimension is D. And look here, dimension of Z is the same as dimension of A. And dimension of A has D number of columns. Each of the column corresponds to each of the nodes in that hidden layer. So that makes sense, right? So in a way, when you look at these hidden units in the hidden layer, it's not one value, it's a vector. And even though all the dots, all the units look like one column, they actually in the data, in the implementation, they represent columns, not one column, but each dot is a column. You put the columns side by side, you get a matrix, right? So, okay, great. So now you know the dimension of Z net input and how you get it. And once you have that, you simply conduct an activation, which is here. Let's use the Sigmoid activation as default to start with, because it's similar to literature question. It's a basis point that we can start. After the Sigmoid activation, the structure doesn't change at all. It simply activates each of the value element-wise on its respective position, and don't change the structure. So by the end, you have a same structure matrix, which is referred to here. It has n number of rows and d number of columns. So now you have the activated value. What does that mean now? Now let's take one element here again. It's the first row, which means I equal 1. The first example, for the first example of customer, the first column, and I said columns refer to different units, the hidden unit. So that means after calculating the net input and activation, the first element in this activated value matrix is going to be the value of this unit, the first unit, for only I equal 1. For the first customer, its activated value of this hidden unit is that value here. So then what does it mean then? That means for this particular unit, based on these coefficients and based on these inputs, it's the first attempt of prediction for this particular customer. It's an attempt to predict, it's one step closer to the ultimate prediction, but it's a sort of a middle level prediction for this customer. It processes the data for one step, which perhaps helps the model recognize something here about this customer with these input values. It extracted some kind of pattern there to differentiate between the customers. So that's what it means. Because this is not the ultimate output unit, I can't say too much, mostly because there are all of these other hidden units that are working together parallel with this unit. So each unit has its own job. Particularly, what job does this unit do? It depends on the data. It highly depends on the data. This is also because a neural network is a black box. You never know which unit end up being the most significant and useful unit to contribute the most to the end. It highly depends on the case. It's case-by-case scenario. So without particular context, you don't know. And without the particular values in the data set, you don't know really. But after you have trained a model, after you have confirmed the model is predicting well, you can go back and trace the flows of information, and you can identify which cell is more important than the others. You can kind of try to interpret what that unit does. But for now, out of context, you can't say too much. Make sense? So that's a hidden layer. And by the same token, you can understand how the output layer does. It's still a two-step process. The only thing that changes is the information inside that flows through it, and the dimensions change. The net input matrix of the output layer has a dimension of not D anymore, but it remains the same in terms of number of rows. All of these have the same number of rows. It's decided by the input data. All right. These are not the weight matrix. These are the net input and activate values. They have to correspond to each of the input examples, row by row. So number of rows always remain the same for all of these 4 objects, but the number of columns changes. For the same layer, these 2 objects share the same number of columns. When it comes to output layer, it changes, but these 2 will share the same number of columns. Their structure, the number of columns will depend on how many units do you have in the output layer, which is T, right? And T depends on how many labels do you have in the target variable. So here, T equal 2. There are only 2 columns. So, but the way it works out is the same. You take the weight of the weight matrix, the output layer, multiplied by the activated value, now serving as the input value in the middle step. And it's the same process. So, what does this mean? I don't have to explain too much. You can extrapolate from what I said previously and, use the same logic to understand here. But here it's closer to the output, right? These values, after being activated, I should say, this is Z, but this is A capital A to denote the matrix per se, lower a to denote the Python code, but they refer to the same thing. A activated value, the matrix, we have 2 columns here, T equal 2, and these are the values that you will use to make a prediction because it's output layer, right? So if this value is point A, then you would predict that for the first label, the probability is 0.08, 0.8, not 0.08, point A. The first label here is not a default. It's not default. So 80% chance the customer will not default. And it's very likely, this likelihood is very low because the same model makes somewhat consistent prediction on two units, these are complementary to each other. One goes high, the other should go low. So, in the end, we'll predict label 0, which means no default with 0.8, with 80% likelihood. So that concludes the forward prop. And because of the simple process of forward prop, I would encourage you to, after you understand how the code works in these 4 steps, I will encourage you to make a forward prop custom function, which consists of 4 lines of code, and then return. Return should be A of the output. Well, no, sorry, return everything, because some of the middle step results are also useful in back prop. So return everything, right? So I will not write these. For the specific example, I was referring to, in the process, there are 4 steps. These lines, each of these, the first line, the second line is printing the result. Each of the first line in each of the subsection correspond to the cheat sheet. So you can compare them and understand the flow. After that, I recommend doing this because you already have the codes, you put them together, define a custom function. Later, when you use it again, you will need to conduct forward prop again. Then using a custom function lowers the amount of codes that you have to write and reduces the possible typing errors and code bugs, right? Helps flows, make the codes flow well. And in the learning process, you can define the function here. Later on, when we talk about improving the model by implementing L2 regularization, you can move this all the way up to the top so that you have the utility functions. We'll also have another utility function, which is a Sigmoid. Here, I'm not going to include the 2 lines of code in the for loop. I'm going to simply use Sigmoid, which some of you also developed successfully using or implemented this successfully in the exam. So eliminate a number of codes, lines of codes that you have to write in the giant for loop. So here, so we finished forward prop. Any questions? I'm going to talk about backward now. Great. So backward prop, much more complex, but still I'll refer back to logistic regression. Let me set a timer to just remind myself. I guess 20 minutes. All right, back prop. Now, keep in mind, let's look at the flow. Let me refresh your mind. Imagine that we don't have this, we don't have the hidden. And imagine that we only have one output unit. So we have the input layer, and we only have one output unit. And what does that look like? That would be like a logistic regression, right? So to refresh your mind, in the back prop of logistic regression, you first calculate error. You calculate error by subtracting your activated value. I use this to write Z-act, but I use A as a short, which should be understandable. A is the activated value of this unit, and you subtract that from the Y label. And we used to have the flag variable Y, so it's only one column. A used to be only a column vector, so good. Error is calculated by using this this formula. It's a distance between your activated value, which is your prediction, from the y label, the ground truth. After you have calculated the error, you calculate the gradient. Gradient is a function between the input variable x, but we need to do the transpose, and a function of x and error, but we used to have a minus sign. If you recall, after we have the gradient, we'll calculate delta, W, which I refer to here. It's the weight vector. Those, or you can say it's the weight vector beginning with index 1, because we used to put the weights with the bias together. Now we separate them just for better clarity of the codes, as well as to avoid mistakes. And so those weights beginning from index 1 is calculated by I think there's a minus sign here as well. Learning rate minus learning rate times the gradient. Very straightforward. And after having that, you update the weight. Weight is weight plus delta weight. And we used to have old and new. Now we don't have them because we have 2-minute weight matrices. It's hard to manage both old and new. So we don't keep those now. So those are the changes. Now, this is the process we do in literature regression, but now the challenge here is we do almost the same with slight changes for the output units as well. Even if we have more than one unit in the output layer, we do almost the same if you observe the codes. I'll talk more about it. I'll highlight the differences, but the differences are minor. The most significant challenge here is how to calculate error for the hidden. To calculate error for the hidden, we need the y value, and we need the activated value. We do have the activated value for the hidden layer for the units, but we don't have the y. We cannot use y directly because these units, they are the middle step results. They are not supposed to be as close as possible to the ground truth y, because we have another layer. So to compare those directly to y doesn't make sense. Of course you can do that, but it reduces the optimization process. It makes it less efficient. So we need a better, more efficient way to sort of the partial out, or to allocate or distribute the amount of error that is here is closer to the ground truth. The amount of error that's calculated from the output layer, to distribute them back, which is why we call them back propagate, is to propagate the errors in a distributive way and in a way that makes sense to each of these units, so that we have a proper calculation of the error in the middle step. And by having that, we use the error and plug into these formula and calculate the rest of the backprop. So the most significant change here is the error backprop for the hidden layer. That's the most significant change. Once you understand this, you won't have any other problem for neural net. All right, so now I highlight a slight difference between the first step of the backprop between logistic regression and here. When we calculate the error of the output layer, it should be straightforward. We used to subtract the activated value from y, but now we do the opposite way. We subtract y from the activated value of we go from output layer first because it's backprop. Direction is from right to left. Keep in mind. So we first deal with the output layer. Error of the output layer, I should say. Error of the output layer is the difference between activated value of the output layer and Y. And keep in mind, this Y is in one-hot encoded format. We have multiple columns here. So the way we do the subtraction flipped. And if you compare with, this is logistical regression, the summary of the steps for logistical regression. We used to do subtracting A from Y, and by using this error, we need to use a negative sign when we calculate the gradient. So now the slight change is that we flip the way we calculate the subtraction. So then when we get to the gradient descent, we don't have to use that minus sign. We will lose the minus sign. For the output layer, that's the only change, I would say. Other than that, this is a matrix, not a column, and that's it. That's the only change for the output layer backprop. So then now let me move on to the hidden layer. The two steps are critical here. Understanding these are key. But also notice that we will also use the reverse subtraction here to get rid of the minus sign in the second step which is gradient. All right, so with this graph here, now I will erase these to talk about the intuition for the hidden layer error responsibility. If error is calculated here, this is logical regression. We'll erase these. And if we have the error now, this error is the neural network error, right? We use the reverse subtraction here. If we have these, how do we get these? Error of the hidden layer. How do we get these? This will happen here by using the error responsibility transfer. How do we transfer? Think of a scenario. If, let's say, we have a Y of I, and the data look like this. This is label 0, label 1. And we have the value of Y for this customer is 0, 1, which means this customer has a value of 1 for label 1. This customer defaulted. All right, that's the ground truth. This customer defaulted. The first unit is going to try to predict the probability of the label 0. And let's say we get a very low probability, which is great, which is predicting well. And for the other side, we have a very high probability prediction for label 1, which is very close to the truth. That's great. So let's focus on this unit. So I think I should have used an example that predicted wrong, but let's try to work with this. So there's small amount of error, but still the error is minus 0.1, right? When you subtract the value of Y from the activated value, you get minus 0.1. That's the error of this unit, right? So how do I figure out the error responsibility of these different units? Imagine that, let's say if this is the case, and when we analyze the weight matrix of the output layer, which is the sides of these lines, we observe that this line, but this is weight. We temporarily don't look at the weight. This is the bias. We disregard the bias for now. It typically doesn't contribute too much error. The error mostly comes from the earlier, the upstream hidden units. Let's say this weight coefficient is estimated to be very small, close to 0, and this coefficient is estimated to be very large, 0.8. What does that mean? That means we can use the width of the line to indicate the weight, and this weight is very small. That means values that come from this unit, the hidden unit, will contribute a great deal to the values, to both the net input and the activation value of this unit. It turns out that the value of 0.9, the activated value of this unit, is largely defined or decided by this unit because of its large weight. That makes sense, right? This is like regression. If a variable has a large weight, which can be positive or not negative, but its absolute value is large, that means that variable is making a big influence compared to other variables for the predicted value of the target, right? So if this weight is large, and you can reason that the amount of error is largely also caused by this unit, just because this unit has a heavy weight, right? In this case, we have a very good prediction, but in case that we have a poor prediction, where if we say that the predicted value A of this unit is 0.1, which is very far from the actual ground truth, which should be 1. So the error here becomes minus 0.9 when you subtract 1 from 0.1. This error largely is also because of this unit, this hidden unit, because of the heavy weight. So you can backtrack the error responsibility by the size of the weight matrix. But keep in mind, you use the weight matrix value of the output layer, which is these lines. These lines represent the weight coefficient of the output layer, not the input layer, right? Because it's pointing to the output layer. So you can sort of mentally, you can think of a way of representing the error distribution of the hidden layer, which should be when you have the error of the output layer and times a weight matrix, a weight coefficient. If it's from the D to T, it's from D to T, and this is within the output layer, the weight matrix of the output layer, right? So again, you use the size of the error of the output unit for unit T, let's say, this is this unit. You use the size of the error of the output unit T times the error or the weight that points from the unit D to unit T, from D to T, and this weight belongs to the output unit, output layer. Then there you go, you have the error distribution for this particular node in the hidden layer. I hope that makes sense. Weight can be used in this way. So in the end, put it in the matrix notation. You will have the error responsibility part, which is the error of the output times a weight, a big W, of the output, but you need to transpose it. Why? When you have a lot of elements here, the dimension of the E out is n by t. Dimension of W of the out is W of out is the dimension of the previous layer, which is D hidden, D by T. So you cannot multiply n by T with a matrix that's D by T. You have to align the T to the rows here. So when you transpose, when you do the transpose, you get a matrix of T by D, then that's aligned. in the end, you get a matrix that has size n by d. This, hold on. I think that's right. Yeah, that's right. The dimension is n by d, and n by d dimension corresponds to whose dimension? Corresponds to the hidden layer, the activated value dimension n by d. They should have the amount of error. The amount of error should be corresponding to the activation, which is the predictive value, right? They should have the same structure. So there you go. This part of the error component of the hidden layer is calculated like that. This part takes care of the error responsibility transfer. By simply one step of calculation, you get the error responsibility of the hidden layer. But that's not the all. You also have to multiply something. And this something is this one. The question is, why do we need these? Why do we need another term, given that we also have the error responsibility for the hidden layer? To be precise, this part that we'll be putting here, the question mark, is not exactly about the error responsibility. The error responsibility is calculated. It's done. The reason that we calculate another part and incorporate here is to reduce the complexity of the next step, so that we finish all the complex calculations in this one step, so that every other step, all the rest of the backprop remains straightforward and consistent with the logistic regression. Make sense? So now let's deal with this. Activation derivative. What is it? To write out conceptually, not the Python codes, but conceptually, the activation derivative, which is the activation of the hidden layer, take partial derivative of the z, which is net input of the same hidden layer, is the activation derivative of the hidden layer. Why do we calculate this? Anytime we calculate a partial derivative, it's calculating it's calculating a slope. It's like a gradient. So this part is actually part of the gradient function of the hidden layer. But we take them out and calculate it here so that we can reduce the complexity of the actual gradient descent function that will look more elegant. Here it's more messy. Because we're already messy, why don't we make it messier and just simply deal with everything in one step? But here, this slope is not the slope of the gradient descent of the cost, or not, at least not entirely. This is the cost, and in gradient descent, this is what we say. Gradient is the slope of the cost function evaluated at the particular value of W. But now we don't have W. We also don't have the cost. But this part is an element of the gradient function evaluated in the middle part. It's kind of hard to explain too clearly, but the reason we need this middle step gradient function part is because, in calculating the gradient of the middle step, we have to calculate the gradient of the activation function as a middle step. If you still remember about linear algebra, and if you were to take partial derivative of x squared with respect to x, how do you do? Or I think another No, that's integral. Yeah, if you were to take partial derivative of x, or derive x from x squared, how do? You do two steps. In the first step, you take partial derivative of the square function, regardless of what's in it. And then you take the partial derivative of the x, which is inside the squared function, right? So this part is similar to that part. When we take the partial derivative of a more complex function, we have to take care of the derivative of the function form before we get to the specific variable inside that function. So this part deals with that. And this part is decided, the function form of this part and the codes of this part is decided by the specific activation function. So if it's sigmoid, it will have one form. The form is, I think it's the, if it's sigmoid function, then the format is a of the hidden times 1 minus a of the hidden. Refer to the cheat sheet. I think that's right. A of the hidden times, but this time this is element-wise multiplication. In Python, it's simply the asteroid multiplication operand. A of the hidden times 1 minus a of hidden. That's this format. This function format is decided by the sigmoid function, which is the derivative of the sigmoid function. If you change the activation function, for instance, we'll talk about ReLU later, and we'll talk about ReLU in the hidden. This format will change. So by the time I talk about that, I'll point that out. So hopefully, I don't think you, at this point, you might not be able to fully understand these and take these, but that's fine. Given more time, as with the literature regression, give them more time, you will be able to understand what it really is doing. So this part that requires the most amount of time to talk about is done. Any questions? No? Great. So then I can talk about gradient. All the other steps of the backprop, beginning the gradient function, is very straightforward. There are only a few things I need to point out. We're good on time. And gradient of the output is very straightforward. Gradient is calculated by multiplying the input. We used to have x, right? X input. And x train, we used to have x train transpose times the error of the, we used to only have one layer in linear regression. Now we have output layer. Now with output layer, there's no x anymore. What feeds into the output layer is the input layer. So we replace that with the activated values of the hidden, right? So to the output layer, the inputs are the activated value of the hidden. We take transpose and dot multiply the error of the output layer, we get a gradient. We used to have a minus sign here. Now with the reversed subtraction, we don't have that. We get rid of that, and you calculate this. Make sure I get it right. It's the A of H transpose dot multiply error of the output layer. Great. So that's very straightforward. That's almost identical, very similar to the linear regression. Gradient of the bias factor is slightly different. We used to say that it's the sum. We take the sum of the error. I think that's the calculation for the bias term, which is a scalar. The bias term of logical regression, it's sum of the error. But here, it's different because we now have a matrix. Now see that the error matrix is not here, but similar. It's here. The dimension is similar to A of H. A and E dimensions are the same. We have n rows and d columns. And we need to calculate, we need to sum over the error of all the examples, but separate the units. We don't cross calculate the units. We keep the different units separate because, by way of the structure, each unit, each hidden unit, and each output unit will have its own bias term, right? So the bias term of each of the unit in the hidden layer or output layer, they are separated. Together, they are put in a vector, but we put them in the row vector, not a column vector, because all the units are stored in different columns. So we need that to be a column as well as the output. We're talking about output bias here. So E out is this one. And the structure is like that, although you will replace with E, not A. The E of the output layer, the matrix, we need to sum over each of the column to get the bias for the particular unit. No, so that will correspond that, but with all the values replaced with E. That's the error, right? So in this way, you can see the similarity between the bias calculation of neural network and the logistical regression. In the case of logistical regression, we only have one vector for the error, so we calculate the sum that becomes the bias. But now we have multiple columns for each corresponds to a unit of the output. So we sum over the columns and becomes the bias unit of bias term of each of the unit. So here what we do is numpy the sum of the matrix, but we have this additional restriction here. We are summing over the columns, not the rows. And the x equals 0, if you've taken my advanced programming course, you must have been bothered by what does this mean really? And in the end, you understood how that works. With all the functions of the NumPy array and the matrix, you have this axis restriction there. Is to restrict the calculation along those axes. And how to understand that? Axis is a dimension. The very root dimension is the rows. It refers to different rows. The secondary dimension is the columns, it refers to the columns. But with axis is 0, it doesn't mean use the same value of 0 to do that calculation. And that way it's a row sum, not a column sum. It actually means, to me, this is the way I understand, axis equals 0 means to do the calculation using this restriction. Using the restriction that is parallel to the axis, which it refers to. Axis equals 0, which means on the side. And when you restrict the calculation parallel to this axis, you are doing the sum over these values. So you can only take the sum of the value in the same column, not across the columns. I hope that makes sense. So, so this is the mentality in dealing with the axis. Later, we will use the argmax. But when we do the argmax, we will use axis equal 1, which means axis equal 1 is this. is do the row with the column wise, but across across the columns of the same row. We do argmax of this column, which takes the maximum value, the maximal value of this row across the columns, but of this row, and identify the index of that value and record the index. That's argmax. I'll talk about that when we go there. So again, the calculation of the bias vector is to transform the matrix into a row column by squeezing, or sort of by summing over column by column. By sum the values of each column, it becomes, it is condensed, becomes just one row. But the problem for NumPy sum is that it will produce an array or vector that has, here it's t. We have t values here because it's the output layer. It will produce something like that. It will produce an array that has t values, but it has only one dimension. It's not a row vector. We must keep the bias. We must keep the bias as specifically a row vector, because we need to later do the net input. We have to add the value of a particular unit to a particular column. If it's a column vector, it will be added to the wrong place. So we don't want that to happen. But with the NumPy default output of this NumPy sum, it will create that problem. So we need to explicitly, I think this is reshape. We have to explicitly reshape the vector, which is shapeless. It doesn't have a shape. It's a single dimension. We need to transform it to a multiple dimension, to 2 dimension, a row vector particularly. And we specify the number of row to be 1. And we ask Python to figure out what is the size of the other dimension and put it right there. This makes sure that you don't have any exception. The calculation will always be right, because Python will make that sure. We'll make sure the calculation is here. Here you can also use t, which is explicitly coded by you. But what if you make a mistake? So by using -1, you outsource the job to Python to make sure that it's calculated right, and to make sure that you don't have any error in the middle of the training. So this step is critical in calculating the bias term. You will see this part in every line of code that calculates the bias, including the bias for the output layer and bias for the hidden layer. You will always see that. So here the difference, to sum up, one is you are summing all the columns. You are not summing to a single value. And make sure that you use the reshape to transform it explicitly into a row vector. So that's the only 2 differences between this and this and the logistic regression. With the gradient of the hidden layer, it's similar. Instead of using A, you will use X now. It's the X training data transpose times the error of the hidden, and do the same thing here by using the error of the hidden. An error of the hidden comes from the previous step. After you have, so here the error of the hidden, to make it explicit, it's the error of the out dot multiply the weight of the output, but transpose, and element-wise multiplication with the act derivative of the hidden. An act derivative comes from this part. All right, that sounds a lot more complicated, but the complicated parts are done. And delta weight, delta bias, exactly the same way you calculate is minus. Don't forget the minus here. The minus is retained. The learning rate times the gradient. Learning rate times the gradient. Learning rate times the gradient. And the only thing that changes is the gradient for the specific thing, for the specific layer. You have the gradient of the weight. You also have the gradient of the bias. This is where things are complicated, right? You have all these different terms. So, you know, even though the formula, the structure of the formula don't change, the specific objects that you put into, this is should be weight of the hidden, bias of the hidden. All of these are different for different values that you put in. Structure remain the same. You calculate the delta term for 4 stuff, 2 for each layer. Once you have the delta, you can update the weight. Very easy. It follows this format, either B or W of the particular layer that, you know, plus equal the delta of the corresponding weight update term. And when you look at the code, it should be very clear. This time we don't track the old and new, so the weight update part becomes very straightforward. Weight of the output plus equal delta weight of the output, bias output plus equal delta bias of the output. And, you know, by the same logic, you get these. All right, so that's the end of backprop. Now we only have to calculate the 2 very classic model performance indicator. One is the cost. We keep track of the cost to sort of review the learning curve, and we keep track of the model accuracy as a model performance metric. Any questions about the backprop? I know you will have questions too about how to understand things, but at least you have a better idea of the flow, and also what's the role of a specific matrix, the weight matrix or the bias vector during the middle of the training. I hope that's clear, and the process is clear. As for very particularly an element of the weight matrix, you know, you may have not been able to fully understand it. We can talk about later. The details, we can delay them. For now, get a good sense of the whole picture of the process. I think you're good for now. Questions? Great. Now I'll leave the details out, and you can review the codes and the cheat sheets. It should be not different. The only difference here is we now use a forward prop function because we have the function, right? Use the updated weights and use the same custom function. It should calculate the cost value using the updated weights and save the cost to the list so that we can keep track of the entire learning process. When we calculate the and the output, one of the output of the forward prop is the A of the hidden. So it should be out. A of the output unit, output layer. One of the ultimate output of this function is the A of the out. So you use that to calculate the accuracy. When you calculate accuracy, you will make a prediction, right? You will use the Y prediction. We will use the argmax numpy argmax, and we'll use the A. This is A of out. It has dimension of n by t. So n corresponds to the different examples. And what's the t? T is 2 here. So what's the 2 value here? The 2 value are the activated value of the 2 output unit. The first unit will try to predict label 0 is non-default, and the first unit is trying to predict 1 label, which is default. So you can imagine that for each row, these 2 prediction ideally should be very different. This one should be very close to 0, and this activate value should be very close to 1 if it's making a good prediction. If it's a default case. For another case, if it's non-default, then the activate value for label 0 should be larger. Activate value for label 1 should be smaller to predict non-default. Hope that makes sense. And the argument max, what does it do is it will take a look at a particular dimension. Now we want it to compare the value on the same row only. So it's this direction. We compare all the values of everything that's restricted in this direction, which is a row. We compare the value of each row. For the first row, we will record the index value of the activation that's larger. So if this is 0.9, this is predicting default, then we will return arg max value of 1 because it's label 1 that's larger. For another row, if we have 0.9 for label 0 and 0.1 for label 1, we're predicting label 0, and it will return the index of this column, which is 0. So that's the difference. And so that for that reason, we'll restrict the comparison on this dimension. We will specify x equal 1 because it's parallel to the dimension of x is 1. Hope that makes sense. Once we have that y-pred, it's a column. It's 1 column. It's a vector. And by using the y flag value, which is created when we pre-process the data, that's why we need the y flag. We compare these, we're going to calculate the accuracy the way that we calculate accuracy before. All right, to sum up, these are the steps, and these are more specifically the product that comes from each of the steps. This looks very complicated. As long as the process remains intuitive to you, after I explain these, you should have no problem understanding each of these. So the only thing to look at now is the training process. By putting together all these steps, we have reinitialize. We have a big for loop here. It's this long, big for loop. And to train the model, I specify 1,000 epoch. And we would like to know how long it trained. So I use a new package here, which will display a progress bar to trace and monitor the process, which is great. So the entire training took 5 seconds, not very long for my laptop. It's pretty good for 1,000 epoches, and it will in the middle it will show you a progress. So when you plot the learning curve, the cost curve, you see that some things conform to your expectation. The model is learning overall, and after several hundred epoches, the learning curve flattens, which means the model is close to the optimal. It's still improving slowly, but the learning rate is not as the speed of improving is not that dramatic, and the curve of the accuracy of the training set remains consistent. But you can notice one thing. You have these oscillations of the learning. Sometimes the model get worse by more than 3 times, and then it quickly corrected. This is mostly because of the gradient descent. Gradient descent, because of sometimes learning rate is too large. It overshoot the target because of the complex surface of the cost function. It's multidimensional, right? We have hundreds of coefficients here. The surface of the cost curve is very complex. It overshoots the target, it destroys the model, but the model quickly comes back. So you are sure that in the long term, the model will converge despite these little things. The next week, I will talk about things that will get rid of these, which is a mini batch gradient descent. Once you implement that, these goes away. That says something about the efficiency of the learning in the process. Why not 7:30? I should talk about the intuition. Any questions so far? And you see that test set accuracy is 92%, which is the same as the training set. Though this model does not have a variance problem, and this model is close to optimal because I know that the data set is separable as much as 92%. The 8% error is not avoidable, or maybe 7% error. The model is 1% close to the optimal. Okay, any questions? Any questions about the flow or something that's different from the literature regression that you don't understand? No? Let me see. Okay, good. Okay, great. So let's open it for a little bit of discussion. Let me stop the share here. All right. So let's talk about how you understand the capability of neural network. To your understanding, how does neural network handle complex problems as compared to single neuron? I'm sure it's something that bothers you, and you must have thought about it, or you may have a good answer already. So let's share with everybody before I talk about my interpretation.
The only difference that I saw was that the net input is a matrix instead of a vector. I know there was a lot more differences than that, but that was the first one that caught my attention.
Right. Technically, yes. And very, it's straightforward to say that if the model is more complex, it can handle more complex problem, right? In terms of more intuitive language and less technical description of the model, how do you think the model is able to deal with complex problem? So think more about what is the neural network doing in terms of its. A neural network is a combination of the little things. And what are those little things? They are logistic regression, essentially. If we implement the Sigmoid activation, it's essentially, think of logistic regression as a piece of puzzle. Then you are putting 100 puzzles together to make a map. So how does that help you deal with a more complex problem? This is going to sort of help you better conceive the problem, that so that later when I talk about the intuition, hopefully it becomes more intuitive and natural to you. Anybody else?
It's going to divide the, let's suppose if we take an example like something related to image classification or something, I guess it would divide the input image into different parts, and it will verify each part for the respective properties and weights, and deal with them rather than the whole image at a time. And then it will club the all the results, and then it will further do the analysis.
So you're referring to sort of image recognition.
Yes.
Yeah, something like that. I think let's see, in that domain of the CS, which is image recognition or object recognition, the network is able to better capture the feature of the image. You know, for instance, if the algorithm is to differentiate cats from dogs, or dogs from cats, with more complex neural networks, the different layers will progressively recognize features, and to advance from little features to bigger features and more abstract features. Eventually, it will be able to recognize and classify the animals correctly. Let's say, you know, the first layer may recognize that more often than not, the cats have more fur, but dogs have less fur or shorter fur, right? Cats typically have longer fur, so their furs inside the image will make the animal more fluffy, and dogs are less fluffy. I guess that's one feature. I wouldn't know this visually. Another feature is that cats, the body shape, the body type of cats is more lumped together. They have shorter legs, but dogs typically have longer and skinnier legs. Their body type are more flexible. Cats are more like a ball, if you think of it. They typically collapse together as a ball, but dogs tend to be standing, and, you know, as well as bigger, of course. But the composition of the body parts are different. That's another visual cue. But else, if you observe the difference of their facial structure, dogs have more, you know, I guess very.
A definitive jaw shape or something.
Yeah, what's the word? It stands out. You know, dogs, their nose stand out, right? It's a dynamic. It's a more, how to say that? I don't know. But cats, their faces are flat. It's more likely to be flat, and that's another thing that the machine can recognize from the images. And all these smaller or, you know, local features of the different animals, if they coexist, then the machine can be better sure that this is a cat, then that's a dog. I think that's how humans recognize, even though we need a split of a second to recognize. For machines, it needs to calculate everything, and the model has to be well trained before it can recognize. So for image recognition, it's easier to explain the difference between complex neural nets and simpler models, because you have these progression of features that can visually that can be visually recognized. But in terms of business problems, it's more challenging to explain what is really different between between a complex problem and a simple problem. So anybody would like to try to explain what might be a simple business problem and what might be a complex business problem, and how is that the complex business problem cannot be tackled by a single neuron, but a single neuron is only limited to the simpler version of the problem. But for a more complex problem, neural nets have a shot that single neurons don't have. If you want to attempt to explain what happens there.
This isn't really a business problem, but I know weather forecasting uses neural networks to process all the
What, a
inputs.
weather forecast?
Yes,
Okay.
I think they use neural networks, and a single neuron wouldn't really work, or the traditional way of processing the inputs wouldn't really work. So they utilize neural networks.
Yeah. So what's complex about weather forecasting, and how does a neural network handle that, to your understanding?
So they have to take into account a lot of different variables: humidity, wind
Yeah.
speed, temperature, even like what time of the year it is. What season it is. So all these variables add complexity to the variable to the model. So neural networks can handle it better than the traditional way of processing.
Yeah, that makes sense. But let me prompt you furthermore. If the different variables, if we know that these, even though it's a long list of variables, if we know that these variables individually, how would it contribute to, let's say, thunderstorm, strong wind, snow, or even tornado, or hurricane? If we know the, let's say, the correlation, let's suppose that correlation represents these indicators quite well. In that case, a linear model, or not a linear, but a logistic regression, which is a linear model, but it does have some non-linear component in it. A logistic regression would be able to do well by summarizing the contribution of each of these factors together to make a prediction. But perhaps not, perhaps logistic regression is not as capable. And the reason could be that the way that each of these indicators will contribute to a prediction of a particular type of weather and its severity is not that straightforward. I don't know how to say, maybe pressure, air pressure. Does it lead to more or less hurricane? Does it lead to more or less hurricane and tornado? The way it contributes to these different outcomes are not that straightforward. Sometimes higher pressure leads to more tornado, but sometimes it reduces it.
Right.
So the key is that there may be a third factor that contributes to their relationship.
So the combination of two variables affects how.
Not only linear combination, but non-linear combination. It's more like conditional factor, right? So in those cases, a single neuron wouldn't be able to recognize very easily. So let me now use one other example to talk about intuition, and let's see if that makes sense to you. So let me share my screen. Whiteboard. I'm going to use a blank sheet here. So MLP, wait, I think I have, yeah, I have a slide here. So MLP here as compared to single neuron. The case is, think about Tesla. Tesla sales. So imagine that you're working with the Tesla sales department and you're trying to develop a model to model individual shoppers' purchase behavior or purchase likelihood for a Tesla. Imagine this is the early years of Tesla, you know. Time goes back, how many years? 5 years? 2015, maybe. The first model, Tesla, should be S, right? Model S. So the sales department is trying to develop a machine learning model to predict likelihood of purchase, and they have got a sample of first-time e-vehicle shoppers. So these shoppers are interested, but not necessarily they will purchase for sure, but they are interested in purchasing an e-vehicle. And at that time, I think it's earlier than that. I think I visited San Francisco in which year? In maybe 2013, and I saw a Tesla there, and that was early years. So this, and you know, they wanted to know the factors, put together this data set that should include predictors. And I think there are only a few predictors back then because of the less complex market. Back then, if you wanted to buy a real e-vehicle, not those hybrid vehicles, you only have one choice, which is Tesla, right? So whether or not these customers, these shoppers will purchase Tesla depends really only on a short list of things. Tesla's brand image. If a shopper hates Tesla's brand, hates Elon Musk, there's no way he's going to buy it. Other few factors may include promotion. You know, how much promotion is available in a particular month. You know, promotion varies across the cities, across the time, across the state. And also, as well as one other factor is tax benefits. Is the shopper able to deduct a big portion of the tax or derive tax benefits by purchasing e-vehicle? You know, in certain years, the government provides 8,000, I guess, tax break for the purchase of e-vehicle. That promotes a lot of the purchasing behavior. So let's use a very simple model that has only two factors. One factor is a tax benefit. The higher, the better. The higher the bar, the higher the scale, the more tax break the customer gets, depending on the particular case and particular time. And the x-axis is, let's say, discount at that particular time. You can imagine that if I have two outcomes, one means the customer purchased, 0 is a dot, 1 is a circle. 0 means the customer didn't purchase. And how does tax benefit affect purchase behavior? The more benefit it is, the more likely the customer will buy. So I would say the points will be higher, the circles will be higher, the dots will be lower. How does the discount affect that? Same direction. The more discount, the more likely, it goes to the right. The more discount, the more likely to buy, and less discount, less likely to buy. But the dot will not come here because these are better tax benefit category. So if you want to draw a simple line, a linear line, you will draw something like that. The number one factor here in early years is the tax benefit. Tax benefit may be a bigger influencer here other than discount, because early years there is not much competition. Discount may not vary too much in a sense, and also the effect that tax benefit have on the discount is going to be larger. Discount is not going to be over 20%. Discount is in the smaller range, but tax benefit can go up to 8,000, which is almost a third of a fifth of the car. So that's a great deal. So in the early years, the factor that perhaps have a bigger influence is the tax benefit. So this line, when you draw this line, it may be more flat because it reflects the fact that the most variations are in the tax benefit. The discount may not vary too much. So this group, you can think of it as the first-time e-vehicle shopper. Their data will likely lie on here, where discounts are not not very good in those years. Tax benefits vary a lot. Then fast forward to now. It's 2020. The same department is still trying to develop a model, but now they have more complex situation. As far as the market goes, you now have many more for a shopper, which now is not the first time anymore, but maybe the second time. E-vehicle shopper. He has much more choices much more options to choose from. There is a BMW. There's almost we even have a Chevrolet. We have Hyundai, we have Kia, Mercedes, and Porsche, I think, and even more. We have Ford truck. So much more competitions. And given the competition, you have more discounts offered by Tesla, but perhaps less tax benefit now because the market has been promoted. Right. So in this case, it's going to be something like this. The more the discount, the more likely the shopper will buy Tesla. The less the discount, the person may buy something else. So not buy Tesla, or may not even purchase another e-vehicle because of some other factors. So if you were to draw a line, it's going to be quite vertical here. The factor that's going to decide whether or not it buys Tesla again is perhaps discount again, and maybe some other factors related to control of the vehicle. This is a simplified version. It may not reflect 100% the reality, but it's it may be reasonable. But so this is the second time e-shoppers. If you put these two together, the data set will very likely have, if it's now, the data set will likely have a combination of the first time e-shoppers and second time e-shoppers, and you probably don't know particularly. So how does the model predict if we have a single neuron and we have a list of factors? What does a single neuron do? It tries to draw a linear line to try to differentiate circles from dots and circles from dots. But for a single neuron, it has to consider all the circles and all the dots. It may have to do something like this. And it will sacrifice a lot of these points. These points are dots, and these points are circles. So these are the errors that the model have to make. The model have to make a substantial amount of error in order to strike a balance between the boundaries of the two outcomes. But the model does not have a capability to sort of to recognize two, highly different groups of buyers. First-time buyer and the second-time buyer, they act on very different decision models. They consider very different factors when they decide whether or not to buy Tesla, and they face very different market conditions. But suppose that you have a more complex model that may give you a leverage. And this is how. If you have a model that has two hidden layers and one output layer, assuming that we only have one output layer, this part is trivial. We can always expand it. But the number of hidden layer is what's going to decide how complex a model can be. So for this guy, for the first neuron, it can be responsible for this group of buyers. It mostly recognizes tax benefit. So the tax benefit weights can be very heavy, and the weight from promotion and all other factors can be very light. This is lighter, this is heavier. So for this group of customers, this neuron, this hidden neuron, is responsible for recognizing these are the first-time buyers, and for that reason, tax benefit should play a bigger part of the decision. But the other the other unit is going to be responsible for this segment of the market, and it recognizes that this factor discount is going to play a big role, whereas tax benefit, it can be very small. So the benefit of having two units here is possibly able to recognize different segments of the market, which represent different ways of making decisions, and can downplay or upplay the same factor differently for different segments. And when it comes together, it will provide whatever is learned from the model, saying, this is the first-time buyer. It will contribute to one way of making a decision. This is a second-time buyer. Or, the model is not going to be 100% sure which one is which, but it will have a proper weight distribution to feed in sort of the recognized decision pattern and to predict the model properly. So that's the way I understand that neural networks can handle the more complex problem than single neuron by using this Tesla purchase example. I hope that makes sense. If you have any questions, let's talk about it. Otherwise, it's a very heavy lecture, I hope that you take away something at least. So anybody want to discuss this or anything related?